Hello, guys. Welcome back. And we have Sayar Karmakar with us. Good afternoon, all of you from India. And Shayarda's time is 3:30 a.m. in the morning. So thank you so much, Shayarda. And for Shayarda, Shayarda has done his B-Stat and M-Stat from ISI, uh, Kolkata, and then he has gone to University of Chicago to pursue his PhD in time series, right, Shayarda?
Yes, yes.
Now he is a statistics faculty at University of Florida. So he will be sharing some exciting insights into some really interesting statistical and probabilistic problems. So let's see what we have ahead in front of us. But we will wait for some minutes, some seconds rather, to for the students and all the people all over the world to join. And I will set some timers over here. Okay. So we're starting in 30 seconds and 1 minute. Let the people join. Okay, guys, welcome back, and let's start the session now. Shad, you have anything to tell to the audience over here, or you want to start right away?
I can start right away. Thank you, Srijit, for the invitation. And it was nice to sort of be able to talk to this audience. I mean, I have not really given a talk on like sort of the basic level time series, and I do teach a class here, and I've been working on this. Interestingly, my background on time series started back in ISI in my MSET first year. Professor Shubir Bhandari, he taught us this basic introduction to time series. But then when I went on to do my PhD, I was initially not sure exactly where to work on, and I have had experience in working in the sort of some genetics problem before that. When I was in IMSTAT first year, between my CSO training and joining the IMSTAT second year, I spent a couple of months at JHU, and then I went back, and then when I was joining back University of Chicago, I was initially thinking of doing something machine learning, but the professors I was trying to get to, they were actually busy because of like they already had a few students. So then I was also doing some like optimization courses at that point of time, and I thought like maybe I would like to spend my PhD journey with solving some theoretical problems. So at that juncture, I came to know about this professor Webia Wu, who was at University of Chicago, and with him I decided to start working. So it's been a long journey in the sense that I've been like the basic introduction of time series. I mean, what I will probably go over, maybe it's known to too many of you. So the way I decided to divide this talk is in two parts. The first part is like some very basics of time series. Even in those, I wanted to sort of give some real data analysis picture so that you understand exactly what sort of series we are talking about, what the basic tools to analyze that. And then moving on in the second half, I'll talk about some of my projects, and then these projects I'll try to explain in a very sort of basic way, not going more details into like all these proofs and theorems, but then I'd like to like show different sort of applications and why I believe learning this autoregressive dependence or like this sort of structure formally has like many more applications than we traditionally think. So for example, the very last slide will actually conclude with a very popular neural network algorithm. But even though it's a neural network algorithm and technically does not have a lot of time series component in it, I will try to advertise like why learning these autoregressive processes can also help in understanding how these neural net algorithms work. So that's the basic structure of today's talk, and I will of course share some interesting data sets, some recent and like some data sets on COVID, some data sets on some of these stock market data or like this pricing indices or like even one data set from Bitcoin. I will not go into like I will not go into how to forecast or how you can become like a trader. Like knowing the, like going over this talk will not help you in understanding where you should invest if you're thinking that this talk is going to talk about that. This talk is more about mostly time series, and then I will talk about some of the application. So the first half I'll spend more on the basics of time series, like why do we even care about this, exactly what do we learn from this, and then in the second half I'll move on to some of the specific projects. So uh, maybe
So
now I will.
let's yep.
Yes.
So can you just explain a bit more about the what you told about independence and dependence to our audience?
Right,
And there is
right.
good morning, Shayur. Invite like wish from I think it's Diganto sir to you.
Okay, yes.
So yeah,
Hi Divantu sir, yes. Nice to hear from you. Yeah.
yep.
Okay.
You can start now.
Right. So I will start here, and like mostly the basic statistics tools that we learn over the undergrad and even the grad classes is that we assume independence, we assume that the data sets are independent. And not only at that level, like we assume independence at so many like papers, in the sense that if you look at like even top journal papers, they do assume independence. So I have just collected one excerpt here, like from one of the papers that came out in JSSB. And even though if you read the if you read the data collection procedure, you will understand that this procedure, like here you're collecting genes from the same person, and typically these genes are supposed to be correlated. Sometimes you collect data over different time period, and but you still assume independence just because it's easier to do the calculation. So one of my, like the reason I've calculated, I've sort of extracted this one out, was to show that like there are many examples where you know that they are supposed to be correlated, but we just completely ignore the temporal order of data collection, or sometimes even like the intrinsic dependence that the dataset might have, because usually dealing with independence is much easier. And one of the things that I want to explore here is like starting from a model of independent data, how you can slowly build to a dependent scenario. And that is exactly what this time series, or like the training on time series, teaches us. Okay. um,
So here, in you have told about neighboring observations. So in terms of temporal, like time, or it's in terms of distance, or
yeah, so
uh,
here, I mean, technically, I mean, it can be anything. Literally, you don't need to restrict yourself to like just the collection over time. It can be collection over like a grid space, or collection over a network, where the dependence is difficult to explain as such, like an exact ordering over time. So the dependence in general can be anything, but what we like sort of prematurely assume is that we assume that these points are sort of independent, and which of course simplifies our calculation. So that's why we assume that it makes our likelihood computation simpler. So that's why these are typically what we do. And like if you see the examples here, like this example here, they are also calculating these estimates based on just the simple independence assumption. But like even in this example, probably the independence assumption can be questioned. So what we will do, like the way we will organize the talk today, we will talk about the basic introduction of time series, what exactly is a time series, and I'll initially focus only on like the collection of, I mean, the collection happening over different time instances. We'll talk about the basics of time series. So we talk about this autocorrelation function, how to test that. We'll talk about some popular time series processes such as autoregressive moving average, ARMA, which is autoregressive moving average, and then maybe just a brief snippet about this arch-arch type of process, which are very popular in econometric models. Then we will talk a little bit about spectral density. So at that point, we'll be covering the basics of time series that we typically use. And then I will move on to some of my projects where I'll discuss like sort of some time varying models. I have like 3 works on time varying models. I'll discuss briefly on that, one project on change point model, and I'll try to close out on like one very important aspect of forecasting. Why do I call that very important? Because like as a practitioner, or like if you are trying to sell your analysis to the industry, or like someone who is more interested in knowing the future, they will say that okay, we can learn all about this data set and the intrinsic properties of this data set, but we are more interested to know what is going to happen in the future. So I have a couple of works in this forecasting as well. So I will briefly touch on that, like why forecasting is important. And then finally, at the conclusion, I will talk about like some general forms of dependence, in the sense that we do not need to restrict ourselves to just a temporal order and like discrete time series where we collect data point at each time point. I mean, collect data set at each time point. Instead, we can have like data set over a spatial grid or like a network. And this learning about this dependence can also help us in learning some sort of autoregressive structure which are used, which are used to build this neural net algorithm. So that's pretty much the organization of today's talk. The basic definition of time series is a collection of observations that are sequentially collected through time. So you have, usually we will assume for this talk, we will assume that they are collected at each time instance. They are like, maybe it could be each day, each week, each month, each year, and so on. So it could be more general than that. It can be irregularly spaced. It can be, there could be missing data, blah blah blah. We will not go into those nitty-gritty details here, but we'll think that this is the most ideal scenario. You have one regular time period after which you collect one set of data point, and you assume that there is correlation in what random variables you observe at these different time instances. Many different applications I can think about, and usually like some of these slides I actually copied from the time series class I designed here. And the many applications that we can think is like in the agricultural field. You can have like some production of some of this um, annual production. You can look at the crop prices. In the business and economics, which is like one of my major focus, you can look at stock prices, weekly interest, forex rates, monthly price indices, quarterly sales, and so on. You can look at this EEG, sound, electric signals, voltage, and then in meteorology, you can look at different sort of climate variables like wind speed, temperature, rainfall, and then you can also look at pollution, blah blah blah, social science, annual birth rate, mortality rate, crime rate. And then you can see, like, you can look at this COVID-19 data set, which is like a huge sort of time series analysis that's going on right now about like how these numbers are changing each day. So typically I would say like time series applications are pretty much everywhere where you can think about where how the data are collected. And then if you think that there is like long enough data sets for like some regular interval, then you can think about analyzing that through a time series model. Some examples through pictures. Here I have collected this is called this hat crude data, where you have northern hemisphere, southern hemisphere, and global. So 3 data set from the year 1860 to I think 2010. And here they usually look at the anomaly of the temperature, keeping the 1860 to 1890, rather I think 1990 to 2010 as the base. So that's why this is where the base is. Like, so somewhere they have the base, and then keeping that base, they see whether it's going positive or negative based on that average. And you can see this is northern hemisphere, southern hemisphere, and global. So the reason I plotted this was that sometimes you do not just collect one data point at each time instance, you collect more than one. So there is something called like a multiple time series, where you try to observe, multiple, like a vector valued thing at each time instance. So that are called multiple time series. So that has two different type of correlation going on. The first one is an contemporaneous correlation, which means the correlation that exists at one time point between the coordinates, and the other one is that you look at different time instances. So when you talk about covariance, naturally that becomes like a covariance matrix instead of one single real number. This is population change, and you can see these are also like 3 different time series that are going on, which is like the plotted here. So usually in a time series plot, you usually plot the time series lengths over the x-axis, and then this is what the data set that you want to plot. And then usually you have, like, if you're trying to advertise 2 or 3 comparable sets, and you try to use different colors, you put a legend here so that you can understand the dynamics of all these 3. So usually the goals are like when you look at a past time series, you can think about, we try to see if there's a trend. If this trend could be seasonal trend, which means there's a periodic component in it. It could be temporal trend, which is like an usual, maybe an increasing trend or decreasing trend. It could be spatial trend in the sense that based on where it's collected, or in the sense like the word spatial here should be taken as like this could be like some exogenous covariates. We can talk about the mean, we can talk about the variability in the sense that whether the on average where the mean is going or the fluctuation is going. Then we sometimes try to do quality control sequential analysis in the sense if there is a change point, in the sense if the trend is going to change, or if you take out the trend, then if you look at the random variable whether there is a change or it can be assumed to be the same, and then you can do this based on like the usual testing, or you can do a sequential type of change point analysis. And then finally, the probably the most important goal is to see where these time series are going in terms of the future. So for example, this is an example from Uber ride when you initially started. And as you can see, daily ridership was going up. So if you remember the Uber thing, I mean, back in US, it probably started around 2011, 2012. I don't know the exact time, but you can see the ridership was going up, and like it was already reaching, like in just 1 year it was reaching like around 200 million. And so these are the future forecasts. So sometimes what you do is you like use a different color to say what sort of forecasts people have for the next few time instances. So these are some of the basic goals. Moving on to the basics of time series, I think one of the most basic thing is to talk about this autocorrelation. So for a stationary process, I have put that inside quote because we do not want to get into the technical definitions of stationary process, but the stationary process you can imagine, which is kind of same no matter at which time point you look at. So for a stationary process, you assume that for a stationary process, you look at the dependence at lag age as expected value, like covariance of xt and xt plus h. So which is defined here. This should be an italic E. And so this is from one of my paper, like an applied paper where we were looking at classification of malware versus benign in a hardware security project, where we were trying to look at this autocorrelation. So traditionally in this project, people have been using traditional classifications, but what we said was like that see, we should look at this temporal order, because when someone is trying to attack one of these hardware chips through some of their programs, they do come at like temporal, like at each time point. And our goal was to see if we can design a mechanism looking at this temporal order, exploiting the temporal order, which has a higher amount of accuracy. So when we were trying to sort of motivate this problem in our paper, we started showing that, okay, if we just look at these numbers that are sent by these outside programs, then you can see that these numbers do show significant correlation. And this is what we used like in this autocorrelation plot. So typically you can see that the autocorrelation plots, they do have like significant correlation. So usually this blue line is the line of significance. Above this, you usually say that, okay, this data set is showing significant correlation. And then depending on how the ACF function is looking, you can probably understand what sort of process this is coming from. So there are definite rules for autoregressive processes, moving average processes, and these processes do have different forms of autocorrelation. And then based on that, then you can probably go in and fit one of these particular models. So
So,
how to formulate?
hello.
Yes, yes.
Yeah. So, our audience may like, just for our audience, one thing I will ask you that this autocorrelation, this function autocorrelation, what does it exactly measure? Suppose it is the question of the audience. So, how
Yeah,
will you
yeah.
tell it?
So that's a good question. Thanks, Reggie. So gamma h is expected value covariance of xt and xt plus h. So if you imagine, if your data set is independent, then only thing that you will see in this autocorrelation plot. So this is actually autocovariance, and if I standardize that, then you will get autocorrelation, which is gamma h over gamma 0. So you can see that. So that's why the ACF function at gamma 0 is always 1. And this autocorrelation function, yeah, I should have probably corrected this by saying this is autocovariance, and then gamma h by gamma 0 is your autocorrelation. And If gamma h is 0 for higher h than 0, then it's an independent process. In the sense, if all these lines were below this blue line of significance, then you would say that, okay, this process probably can be assumed to be independent across time rather than going for like a more complicated time series model. So this is sort of like a basic visual check where you would understand whether at all you should go for time series. Okay.
Okay, so I have one question personally that
Yeah.
so this is a week what you can assume that the in around h to be very small, if h is very small, the relationship between xt plus h and xt can be approximated by linear, and therefore correlation may make sense to like induce independent aspect. So like for higher h, if it's like below, like within the significance region, like then how he can tell it's independent? Like we are telling
No,
linearly
no,
independent
we
aspect.
will not be able to tell anything about whether the process is independent or not. But what we are trying to see here is that, like, what sort of time series should we plot? In the sense, whether we should at all plot time series or not. Like, this is not a formal test. Like, I think where you are coming from is that where you are trying to say, okay, if we see observed value, like these are estimated values. So these are estimated value of gamma h over gamma 0 hat. So what you are probably trying to say is that how do we know if this is below here? How do we know, let's say, xt plus 9 and xt are independent? We do not know actually. What I'm saying is when you have a data set and you know it's collected through time, what we initially see is that whether there is at all any dependence. So the very first thing we do is that we try to plot an ACF function and then try to see what sort of ACF is we are getting. If we see prematurely everything is like below this, maybe we can say, oh, there is no strict dependence here, so probably it's safe to assume independence, and then we can of course formally test it. So I'm not saying, but just looking at this visual plot you would be able to conclude there is independence. We won't be,
So
but
that is always the first step, right, Sharda? Like we
yes.
check the independent dependence based on the ACF. ACF, by the way, it's autocorrelation function wala plot. We check this plot and we understand the dependence, right, Sharda? This is what
Right,
you're telling.
right, right. So that's like the very first visual check that you run, like to understand whether at all you need time series, and if you do, what sort of time series
So it's a
model.
exploratory data analysis sort of idea.
Right, right.
Okay, okay.
So then moving on, this is like sort of way to formally test this, in the sense that if you want to formally test whether there is a correlation, there is a test called Durbin-Watson test, which usually does the tests for, I mean, autoregressive processes of order one, but it can be generalized to further scenarios, and you can see these ET hats are residuals from a regression, and then this is the formal test statistic, and based on that, like the data set that I was showing, you can see that the p-values, like the histogram of the statistic values, were like between, like prematurely between 0 to 2 and not much between 2 to 4. So typically if there is no correlation, it should be centered around 2. If there is positive correlation,
So
it
can
should
you go back to the previous one so that like just take one example and see, yeah. Can you just take one example? Let's say auto benign wala example, CM benign, and can you go back to the other statistic wala example, like
No,
where
no,
it's
these,
not.
these are not related, in the sense this is
Okay,
like
okay, okay, okay,
just for one particular subset of the data set. But then what we did was we looked at all the malware data and like tried to look at the ACF function there, and then not the ACF function, we computed the D statistic there, and then based on that we computed its p values and we computed this. So you can see prematurely everything had like a very low p value, and like a majority of them are actually exactly zero. I should have probably kept a bar at 0.05, but these were all kind of zero. So then here you can see both of them are like showing the histogram. The values of the statistics are positive, which says that there is significant, like are not positive, are on the left side of 2, which says there is a significant autocorrelation that is in the left hand side. So that's one test that you can run, in the sense if you have multiple instances of this sort of time series, then you can run this sort of test looking at this d value, and then this t statistic. If it's prematurely between 0 to 2 and probably left skewed, then you can talk about, okay, there is significant positive correlation. If it's just centered around 2, maybe lying between 1.5 to 2.5, then there is not a lot to worry about dependence. If it's prematurely in the region 2 to 4 skewed to the right, then you can talk about, okay, there is a negative correlation. So that's pretty much one way of formally testing how. So this is a formal test for existence of correlation. So
Okay,
now
okay. One question is there from
yes.
the audience. Ratnadev was asking why gamma zero in the previous auto covariance function is zero. Is one. Sorry,
Yeah,
gamma zero
yeah.
is
So
one.
as I mentioned, these are like, so this is probably, I should have mentioned, this is as
Auto.
covariance.
Yeah.
And what we are plotting here is autocorrelation, which is gamma h over gamma zero. So that's why no matter what your gamma h is, you always divide by gamma zero. So the first one is gamma zero over gamma zero. This is just a standard way of standardizing everything, so that you always start at rho zero equals one, and then you look at its relative values. So in that way, it's easier for us to give this sort of significance limit at point two. Okay,
Okay,
this is
yeah.
not
Got it.
exactly point two, by the way. It's a little less than point two. But yeah. So that's this is autocorrelation and not autocovariance. So that's why it's always starts at one.
Can you go to the next slide once, previous
Yes,
slide once? So
this
for the
one.
students who are learning just the statistic, I mean, yeah, this one. For the students who are just learning hypothesis testing and basic stuff, they can think like how the value of D can, why it implies positive correlation. Like it's told here that if D is less than 2,
Right.
then positive correlation
That's
is
not
true.
too difficult to see, in the sense that if you sort of expand this, you would
Yeah,
see
yeah, yeah.
that if you expand this, then you would see et hat square, et minus hat square, they are roughly equal, and then they would cancel with this one. So that will give us the standard value of 2. And then if you look at the cross correlation, which is 2 et hat, et minus 1 hat, and since et hat, like et hat is a close approximation to et, which already has mean 0, this 2 et minus 1 gives us a correlation. So based on whether it's positive or negative, this value will be bigger than 2 or lesser than 2. Okay.
Very good.
So that's the way you can look at this d statistic value.
Yep. Okay.
All right. So some popular processes we have, I mean, autoregressive process, moving average process, ARMA, the train plus seasonal component model, and then arch processes. So I will jump right into these processes. AR process, yi is rho 1, yi minus 1 plus ei. I called it AR process. This is just one simple example, but this could be more general than this, in the sense that it could be yi rho 1 yi minus 1 plus rho 2 yi minus 2 plus ei. But this EI process is like sort of a background white noise process, where we assume this process is independent. This process does not have any sort of time dependence. But if you look at this one, this is called autoregressive process of order 1, because yi depends on yi minus 1 directly. So this sort of process, so you can imagine the value of rho 1 controls a lot, in the sense that if value of rho 1 is close to 0, or if it's exactly equal to 0, yi is just ei, which is like a white noise process, no dependence whatsoever. So it just has independent increment, like independent observations at each time instance. However, if your rho 1 is positive, then each time yi is actually dependent on yi minus 1. So these sort of processes are extremely important, in the sense that if you have an increasing trend, usually the things increase because these yi values are somehow motivated by yi minus 1, or sometimes both yi and yi minus 1 are motivated by the same sort of exogenous variables. So that's why these sort of processes are extremely important, and typically in real data sets we see rho positive, in the sense there is like sort of positive correlation. That is more natural to happen than negative correlation. By the way, whenever I mention I here, I mention I to be the ith time point. And typically you would see alternative formulations in Wikipedia or in textbooks where they use the letter T to symbolize time. Okay. So for a moving average process, however, the definition changes a little bit, and it is only moving average of this white noise processes, which is ei plus theta 1 ei minus 1. But somehow there is a connection between these two, in the sense that you can see yi depends on yi minus 1, and here also yi does not directly depend on yi minus 1, but yi and yi minus 1 are correlated through these ei variables. So this sort of autoregressive processes and moving average processes are sort of the building blocks of basic linear time series. And then moving on from these processes, we have this ARMA process, where you have both the components. It could have one autoregressive lag, and then it could have one moving average lag. But then these are all like the very basic example. It can have multiple lags as well. So if you have like 3 lags, it would be rho 1 yi minus 1, rho 2 yi minus 2, rho 3 yi minus 3, and then you can have 2 lags of here, which would be ei plus theta 1 ei minus 1 plus theta 2 ei minus 2. So in reality, this series actually do pretty good job, but then there are series that we need a little bit more complicated series, which are like non-linear, in the sense that it is not really, it does not have this linear structure in them. So here I wanted to just give a very basic introduction to like a basic nonlinear process called an arch and Garch process. And I'll mention why it's called an arch process. So yi, instead of being dependent on yi minus 1 on its mean, now it's called sigma I times xi, where xi is a normal random variable, but this sigma I depends on yi minus 1. So in the sense, the variance of yi is conditional on the value of yi minus 1. So that means if your yi minus 1 is large, then your variance for the next one is large. If your yi minus 1 is small, then for the variance for the next one is small. So this model, like a bit of story on this one, this model was introduced back in 1982 by Robert Engel. And interestingly, this paper got like probably 5 years to get published. But then once it got published, it became extremely popular. And the reason these processes become popular is that they do fit many real life data sets. And I mean, it became so popular that Robert Engel ended up getting a Nobel Prize back in 2003. Um, then his PhD student actually extended this arch model to Garch 1.1 model, where they introduced one additional recursive parameters. Okay. Now, one interesting thing is for these processes, they do have very distinct sort of ACF and partial autocorrelation plot. So the good thing about that is you can look at this autocorrelation plot and have a basic understanding whether you should go for autoregressive process, or you should go for a moving average process, or you should go for something like an arch or Garch process.
So can
So
you give an
that's one.
example of the arch process in the real life, like where the
Yeah,
any
so for
example?
example, like the daily log return of any stock indices is the yi value. So in the sense that if you look at the log return of, let's say, the Bitcoin data, I will talk about that. Or like any sort of stock index that like when you look at the log return data, that's a mean zero data set. And then if you look at this data set, then this sort of data sets are modeled through this sort of arch processes, where you assume that this is dependent on the previous lag. Typically, it's been standard to analyze them through Garch process rather than arch process. And you have these three parameters. You would like to estimate this mu0, a1, and b1. So the yi will be the log return data set. And then using the log return number yi, you try to like estimate these quantities mu0, a1, and b1. So this is pretty much like that. That's one example, but I will touch upon that later on in my slides. So as I was mentioning, there could be simpler models which can have like an increasing trend plus a seasonal component. In the sense, you can see this is like sort of chicken price data, and I don't know exactly which market they were talking about, probably the US market. And you can see these all these data sets are collected from this Chamois Stoffer book, and this is a very nice book which is publicly available, and they do have a available package as well. They do have an edition for R packages. So one of the cool things about this was I also did not know about this when I was learning time series back in ISI. But this is what I learned when I was trying to teach this class, is that this book has a very nice, it's an exploratory book. It's an preliminary like textbook which you should read. And they have like a parallel R analysis book as well, where you can see multiple data sets, where you can try your own hands and see what is going on. So you can see here there is a strict linear trend here, which is like increasing linearly, but around that line it is showing some sort of pattern here. So there is some sort of periodicity here. So every 5 years there is a periodic pattern, and then it goes up, it goes down, it goes up, it goes down, it goes up, it goes down. So these sort of processes have like two types of components in the model. So this G is the trend, the MI is a periodic component, and probably the period is around 5 years or so. And then you have an white noise process EI. So sometimes our goal is to identify this linear trend, or like it could be linear, it could be quadratic, it could be something other than that. But then after you get hold of this linear trend, then we try to see if there's a periodic pattern. After you get hold of that, then you get to EI. So one of the goal is to break down the dependence in multiple components or these parameters of these autoregressive processes. So that's kind of one of the goal, to understand the dependence. So we are trying to get a data set that we know is dependent by just the context of it, and then we try to understand what is the nature of dependence. Is it like a model like this? Is it like a linear model? Is it like a non-linear model like Arch and Garch? So these sort of questions are always there. And one basic introduction to that is just go and plot the ACF function of the data. That gives us some insight. So what I would say is, like, you can try this problem on your own. Like, you can just install the ASTSA package that has multiple time series data itself. I mean, inside it, so you don't need to collect the data from outside. And then you can run these sort of functions to see whether the ACF function will be able to catch that or not. Or once you can estimate the G, you can take a regression component out, and then you can run the ACF function to understand the difference.
Can you
And
repeat the
then
problem again? Like, what we get the data set? I'm just writing down it for the people
yeah,
out
yeah.
there.
So this ASTSA package, and then if you just search for this time series application, this TSA4 book, this Shamu Stoffer book, you would be able to get this resource online. And then the book has very nice introduction to all these basic time series that I'm talking about. And they also have like a parallel R analysis. So there you can get all these basic data sets. Okay, so that's one book I would recommend. And
Okay.
maybe before I move on to some of my own projects, I will just touch upon the spectral density. So in a spectral density, it's like, if you we have already introduced the gamma h function. Based on the gamma h function, if you look at a combination of gamma h like this, then this is called spectral density at the frequency omega. And this f of omega, if you know f of omega, you can recover the gamma h. If you know gamma h, you can construct f of omega. So this is like a Fourier type of analysis on time series. So as you know this, I mean, if you know gamma h for every h, that kind of characterizes a time series. Similarly, if you know f of omega for every omega, that characterizes a time series as well, because using the f of omega, you can construct back the gamma h. So this is like a Fourier transform, inverse Fourier transform type of relationship that you can have on time series data. So sometimes, instead of going into the gamma h, we look at the spectral density, and based on the spectral density, we do a lot of other analysis. So that's just why I wanted to touch upon that. So this is where I will sort of draw curtains on the basics of time series, and I
Okay,
will
one
try to.
question on the basics of time series
Yes.
is that Rith is asking that how AR and MA model relate trend and seasonality model. Are they used independently or not?
So usually the AR model and MA model, here there is no trend. Whatever trend you have yi, the trend is on yi minus 1. So typically you can have a trend component outside this. I was just mentioning this because these are like mean zero processes. But when you actually collect a real data set, that might not have mean zero. So that might have a higher mean, or the mean could depend on exogenous variables. So that is the trend process that you first try to eliminate. After you eliminate the trend, then you look at this mean zero residuals that can have dependence within it, and this dependence is modeled through this autoregressive or MA process. So typically the trend is kept separate from this sort of modeling.
Okay.
And with this chicken price data, as you can see, if you plot the spectral density, then you can have this sort of spectral analysis where you can have this periodogram, and this spectral analysis, they do show spikes at, I mean, the periodic pattern. So there is a spike at 1, there's a spike at 0.2, which is 1 over 0.2 is 5 years. So it can give you insights about what sort of periodicity the data set has. Okay.
So what is the spike in? So spike has a relationship with the periodicity.
Yes, yes. I'm not going to deep into the exact why it does so, but that's like sometimes used to understand the different frequencies. So more, if you ask me like why exactly we do that, so sometimes there could be multiple periodicity that work together. In the sense that for the chicken price data, let's say you can have an annual period, you can have like a 5-year period, like you can see in this data, but based on like the season of the year, you have like an annual period. So if you have multiple periods periods that act together, it might be difficult to identify them through the raw data. So sometimes we go to spectral density to identify what are the important frequencies. Then once we recognize the important frequencies, we invert them to get the period length. Then we try to go back to the actual context of the data collection to understand why exactly these periods are there. Okay.
Perfect. Okay, so one question from my side, just basic.
Yes.
Okay, I will take 2 minutes. Is that as I just trying to understand for the audience, like what is I'm trying to understand the whole procedure. First, we get the data, and then we do the ACF to understand the dependence and stuff. And then, as you have told, for seasonality, the understand the periodicity, we can do this transformation, spectral density transformation, and understand the seasonality. What are the corresponding periods? And to understand the trend, we can fit normal regression models, right?
Yeah, you can fit normal regression model, but like if you assume just normality, that might not be true because this autoregressive processes like this AR process is not exactly normal because you when you do normal regression, you assume this EIs to be independent. So there is where it could fail. So you can do a linear model, then you can plot the residuals, then you will see the residuals or like do just an ACF plot on the residuals that can show dependence. So this is where it would fail. So there is a test called Jung box statistic that usually people do to check for diagnostics of a fit, where you would look at this dependence like after you fit any linear model to see whether there is dependence there. So at the very bottom of a Jung box test statistic, you can look at the p-values, and then these p-values, if you see all the p-values are bigger than 0.05, you should be happy. But if you do not take care of the dependence inside your model, then they might show dependence. So sometimes what you do is if you just run like linear regression, you can combine linear regression and some forms of ARIMA type of models inside the error together, and then you can fit that. So this is usually done through this sort of SARIMA type of packages where you can fit both the dependence and the exogenous covariates together. Okay. So the
So okay, so
goal is
the
to
errors are
probably
being
understand, sorry, the goal is probably to understand whether there is dependence or not in the EI part, in the error part, and not on the trend part. The trend part is separate, but like if you take away the trend part, then whether there is dependence in the error part, because that can change our estimate for the trend part also, or the estimate for the covariates also drastically. So that is where we try to draw a statistical conclusion whether a particular covariate is significant or not. So we would want to make sure that our estimators are not confounded by the intrinsic dependence that is there in the error part. So that's why it's important to understand, even when you fit like a linear model where the units are collected over time, whether there is dependence or not. Okay.
so yeah. One question Rothendev is asking is how in real life data we and analysis and time series practicality how we can separate this trend and periodicity and error term. Like how
Yeah,
do we?
so that's a good question. I mean, if you look at a data set, then if you see that there is a trend, one thing is you can do is there is an estimator called a Priestley-Chow or Nadaraya-Watson estimator. So that typically gives you the trend. Like so, if the time series looks like this, so I will go into, let's say, yeah. So let's look at this time series. So if your time series looks like this, you can look at like another Watson estimator, which is like a kernel-based estimator, which will give you the basic trend. Once you remove that trend, then like subtract that trend, then you can have fluctuations around zero. Once you have fluctuations around zero, this is where you can assume that okay, we are now at the error component part. Then you try to analyze different sort of ACF functions to understand how these errors are behaving. Whether there is a variability that's increasing over time, then you can go for arch-Gauge processes, or the variability remains more or less constant, and then you can go for like an autoregressive process or moving average process and things like that. So first you try to do the trend fit, maybe by visual inspection. For the chicken price data, it was more like linear. For this sort of data, it's probably something quadratic. You do not need to restrict yourself to that, and I'll talk about that briefly in one of my project. Like you do not need to assume one particular form of trend. You can just estimate the trend itself by as like sort of a kernel moving average type of process. And then once you estimate the trend, get rid of it, then the rest of the component can be modeled through, like then you can run this ACF function type of tests to understand what sort of dependence is left there. Okay.
Perfect, perfect. So yeah, all this ACF function and stuff, all the models, are to understand how the error terms work. the
how the error
dependence
terms
factor.
work, whether there is dependence, because
Exactly.
if there is, then this might sort of, I mean, this might contaminate your estimates for the other components, which are more important, but this dependence factor can ruin those estimates in some way.
Exactly.
So moving on, this is like this is more theoretical in the sense how you slowly build from an independent model to a dependent model. I'll not go a lot into this, but starting from just IID normal 0, 1, you can take linear combinations of that, and then if you take linear combinations of this just taking linear combinations such as EI plus EI minus 1 makes it a dependent process. Even though you restore the mean at 0, it makes it a dependent process. Then that simple type of linear process can be more generalized into a more general nonlinear function. Then you can talk about non-stationary process where this mechanism can change across time. And then you might have multivariate process where you can have multiple different instances of this sort of processes at one time instance I. And a lot of my theoretical works are dependent on like this sort of functional dependence measure, which kind of extracts these analogs of AI, which measure, or AK, which measures the impact of epsilon I on epsilon I minus k. So again, this is a sort of a theoretical thing, and you can probably look into some of my papers to understand this structure mode. This is also there in my, I mean, my thesis where I try to explain this, but this is how you slowly build from an independent model to dependent model. Now, the one of the major focus of my research, like I'll try to wrap up in maybe 15 minutes. One of the major focus of my research was on time varying model. So a time varying model, even though in any time series you do see a lot of time variation, it varies over time. That's why it's called time series. But we will like sort of distinguish that from the models that we previously discussed. We will call all those models a time constant, and the time varying model are models where you assume your parameters are also changing, in the sense that if you have yi is rho yi minus 1 plus ei, this rho does not remain constant throughout. That's much more realistic because, as you know, so this is the daily COVID count data in US for the first few months, and you can see the way this data set has proceeded, like progressed, is very different in different stages of pandemic. And this means like if you just fit one single AR1 model, that does not do a justice to this sort of data set. So that's why what we instead use is like we try to use a model where we assume the parameters, the rho parameter or this theta parameters, they change over time, and this sort of models are called time varying model. This is the Bitcoin data that I was so this is back from my job talk back in 2017, December 2018. Now the Bitcoin has went up to like 62, 63. And interestingly, it went up in that year 2017. It made huge ripple. It went up from literally 0 to 20,000 in just 1 year, you can see. And then it fell down in around 16,000. It stayed there for a while. And last year again, it went from 16,000 to 60,000. So yeah, so this sort of data sets, it is unfair to like just use like one single model, one single arch model or Garch model to model this, because they would not be able to do good justice when there is a lot of volatility. So what we instead proposed was like we will analyze this sort of data set through time varying model where the parameter set will change over time. So we will not restrict ourselves in understanding one single parameter for different chunks. We'll rather make it flexible by allowing the parameters to change itself. So, uh, so this variability is changing as time progresses, and these classic models do not capture like the actual restriction, like actual variation, and we do not call this as like time varying model. So the time varying models are used like somewhat like this. So in the sense, if you have yi as g plus ei, where g is like just a basic one single constant, you can think how do we go from g to g of I over n. If you allow to go from g like one single number, then you can allow to go from g to g of I over n. This g of I over n is more like a trend component. Then you can allow your covariates beta to go from beta to beta of I over n. In the sense, the ith covariate, the impact of it is changing over time. This n is the number of time point that you are collecting your data set on. So this autoregressive ARCH process with order 1 can also change from A0 to A0 I over n, A1 to A1 I over n. Then
So I have a
for the
question.
COVID type of data set, sorry.
Yeah, I have a question. Is that there's so many parameters? Do we use like some sort of like to reduce the number of parameters or something like that by
No,
using phenomenons?
no, actually not, in the sense that we look at there is we just plot this a0 I over n. So I will show you a picture where you I will show how to estimate this entire function. So instead of one single parameter, you can think, okay, now we have like so many parameters, but instead of a0, now we will just plot one single function of a0, which will also vary over time. So this sort of modeling is more general because you can also have this function to be constant. We will do hypothesis tests where these functions are constant, and then you can reduce the parameters to one single parameter. Okay, but to begin with, we do not assume the functions to be constant itself. We assume that these parameters can evolve over time, and then we sort of go back and see whether these functions do evolve over time or they are like more flat, and then we sort of fit a more restricted model by just one single parameter. So this is one of the analysis of the USD GBP data conversion, like the conversion rate. And you can see there was like, so this is the log return data. So when you look at the log return data, log return is yi minus 1, or like log of yi over log of yi minus 1, log of yi minus log of yi minus 1. And when you do that, then it becomes almost like the relative change at each day, which makes it a mean zero process. So you can see there was a lot of variation here. And what we were trying to do is we were trying to plot this a0 and a1, and you can see this a0 function, they do show a lot of variation here, and the variability increased here, which is kind of same as where the variability increased here. But a1 somehow did not vary a lot, and probably it is possible to fit one single line through this. Okay, one single line through this. When you look at the ACF function for the squared data, you can see the ACF function does not die down until like lag 35, and the ACF function of x square is showing significant correlation. So for these econometric models, if you want to understand whether there is an AR arch type of or like arch type of effect, then you do the ACF plots on x squares instead of just x, because as you can see, yi has the square root structure. So you look at the ACF of yi square to first understand whether there is autoregressive processes of like this, and then you try to estimate this function. So doing this, like, so this is where I say like I keep it objective, in the sense that I do not assume any specific model for a0 or a1. But once I fit these bands, then I can look at whether these bands include a horizontal line or a linear line or a quadratic line, and blah blah blah. And that can give us more insight about how we can sort of model this and reduce the number of parameters. Okay? So this is what is the crux of time varying model. The time varying model should allow you to test for a general type of model where you allow the functions to evolve over time, but at the same time you would want to understand whether there's a possibility or potential to reduce it to like lesser number of parameters, to a model with lesser number of parameters. So this is one basic sort of analysis
Okay, I
that
have a
we do.
question, simple
Yes.
question that can you go to the previous slide? Yeah, in the a0 you're assuming it to be once we assume it to be time varying, we cannot like it's like in the second one, a1, you have assumed that it's almost like constant. Maybe we can assume that, but in the a0 you're telling it's varying over time. It's very like diagrammatically it's very understandable. So my question is that all over the time we will assume it's time varying. That's my question, because all of the time many variables will be, many parameters will be coming up. For
Yeah, yeah.
example, like
Sorry, yeah, complete the question. Sorry.
before one part it seems to be like initially it's increasing, then it's decreasing, and then it's time like it's almost constant, right? So can we somehow implement this in the model, like?
Yeah, so you can always assume. So what I'm saying is, when we are trying to plot this, these are the simultaneous confidence bands. So the goal of simultaneous confidence band is to keep it objective, try to understand the dynamics of these parameters. Based on this, Someone might say, okay, how about we fit like a linear component for this, a linear component for this, and so on. But we do not probably need to do that sort of analysis, in the sense that, like, if you are at 1999, you don't really care about what happened in the beginning. But what you do care about is like whether there is a sharp drop here, and like if this drop is happening due to some other economic variables at that point of time, they're like other sort of political decisions, blah blah blah. But however, if you look at A1, the A1 actually, even though it shows variations, like if you see like the confidence bands, they are wide enough to fit a horizontal line through them, then you can say, okay, we cannot reject the hypothesis of constancy, of time constancy. Then you can go and fit like a more more, what should I say, a reduced model with one single parameter. Now imagine this could be like maybe time varying here, and then it could be like a constant here. So in that case, you can fit like sort of a time varying model with just two constants. And but then the question would be where exactly it changed and things like that. So this sort of can be again used like a very first visual analysis, where to draw or like simplify this sort of model, how to simplify this sort of model. Once you look at this, then you can get some insights. Okay.
Okay, okay, sounds good.
So this is the true function, and then this is probably the estimate, and like this is the estimate you do sort of some sort of kernel smoothing average. This is like a Gaussian analog of this estimate through some sort of Gaussian approximation, and then you can create this Gaussian approximation many times. These are the black lines. These are the black lines of like these lines are the confidence bands, and then you can see the blue line is still within these black lines. So looking at this black line, then you can try to take a call whether you can fit a horizontal line through that, whether you can fit like an increasing line to that. And that can give us insight about how to make more specific model, how to assume more specific models for your actual data set. So that is kind of take home message for this sort of simultaneous confidence bands. And we extended this in a Bayesian front to this count value time series when we are trying to analyze this COVID data sets. And like why this sort of model? Because we wanted to build a model which only requires the data set itself and which does not require other exogenous variables. We wanted to understand the incubation period of COVID-19, which is usually like 4 to 11 days. Like, so after you are exposed, takes around 4 to 11 days to for the symptoms to show up. So we wanted to see whether these particular lags were important. So this paper, like initially when we sort of had like a lot of analysis on this is up in archive. Initially we had analysis of a lot of cities and the countries, but that was in the very beginning. After that we wrote like sort of a theoretical paper out of this that just came out in EJS. And this paper has this nice little model like this, which is a Poisson model, which is not exactly this arch-arch type of model. But in this Poisson model, you can see the intensity parameter is time varying in this sense. So we build like the posterior credible intervals for these parameters in the somewhat in the same way we build like simultaneous confidence bands, and to understand what sort of variation do they show, whether they vary over time or not. So the previous part was more from a frequentist point of view. This was more from a Bayesian point of view. So then a few other projects I'll just
So
briefly
just
touch
1 minute,
upon.
just one
Yes.
second, just to make those people who are in still undergraduate. Can you go back
Yeah.
to the, yeah? So here you understand this incubation period of 4 to 11 days. That is the seasonality component, right?
No, 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 no. I have
Okay.
not assumed that. So you typically when it like last year around this time, what people were saying is like you won't show the symptoms right after you get exposed. So what we said was, okay, if you look at a model like this, and you allow number of the lag parameters to be high enough, then probably you would see that the first few lags are not that important, and the lags from 4 to 11 are probably more important. There is always like a weekly effect because in the weekends there
Okay,
is
okay, I
not
understand.
many type of not many tests are going on. So what we wanted to see was, do we also see an effect of incubation, in the sense if xi is high, that probably means xi plus 4 would be high as well, or xi plus 5 would be high as well. So that would mean that this ai parameters would be high as well if I is 4 or 5. So that's what I mean. There is no periodic component here. Like you can of course do like a more fine analysis here by introducing another periodic component.
I mean, you mean
But
A4 or which
sorry.
parameter? So how do you measure that A4 or A11? Like,
Yeah, yeah.
Four.
So A4, A5, these components, like 4 to 11 was just from this initial news reports where they said
Okay,
that
okay.
like it
Got
could
it.
be like 4 to 11, like days before you show up the symptoms. So that is why there's this 14-day quarantine thing because of this 4 to 11. Then they reduced it to 10 days. Some other data sets, like I was saying, this is one other project we are analyzing this sort of climate data where there is a trend, there is a periodic component, and interestingly, even if you look at the annual scale, they do show an interesting period around 60 to 70 years, and that's what we also see we when we analyze this sort of hat crude data that I initially was showing. Uh, some of this, I mean, probably we do not have time. I'll try to wrap up soon. The invariance
It's okay.
principle.
We should complete it. Okay, it's okay. People can.
Yeah, but yeah, okay. So for an invariance principle, we have when you remove like the two pieces of chessboard. This is where I start my this sort of Gaussian approximation talk, where we talk about the CLT type of processes. That if you remove two corners of a chessboard, in how many ways you can fill the rest of the board with 31 dominoes. So anyone who has basic, like we have started with any sort of Olympiad problems, you would know that it's not possible. And the reason is there is something called like an invariant that does not change. Here in this case, it is the number of white and number of black squares that does not change. So there is no way you can fail this. So what is an invariant principle for statistics? So we all learn about CLT, central limit theorem, but we don't understand it is some kind of invariance principle, because if you look at the data set x1, x2, xn, IID, you do not need what exact distribution it's coming from. You would know that Sn over root n, where Sn is the partial sum x1, x1 plus x2 plus xn, the partial sum, the normalized partial sum will go to normal 0 sigma square. Now this sort of CLT processes are called like this sort of CLT processes are like the invariance principle, in the sense no matter what distribution do you have, you would always get this sort of results. But the questions are, how do you relax this identical distribution or independence? And like there are different forms of CLTs there. Now if there, can you extend this to multivariate where you have this multiple time series, only Sn is close to Gaussian, or all the partial sums like x1, x1 plus x2, x1 plus x2 plus x3, or x3 to x10, all these partial sums are actually close to Gaussian. And there are a lot of results that there are, like rather than just CLT. So CLT is just very basic standard and probably the most important result. But around that, people have relaxed this over the last probably 5 decades to get to more interesting forms of dependence, or more interesting forms of theorems, or like forms of central limit theorem, where you can have more general assumptions. So one of my very theoretical project, the first project actually I did during my PhD, is that we approximated all these partial sums with a corresponding Gaussian analog. And I mean, just a quick insight about why it's important to control all the partial sums, because we want to build a simultaneous confidence band and not a point-wise confidence band. So typically what we are taught in the class is about these confidence intervals of mu. These are all point-wise bands, but we want to build like the simultaneous confidence band, which can talk about the simultaneous probability of this band covering the true parameter. And this sort of, I mean, this sort of results require you to control all partial sums and not just the final partial sum. So that's why the one of the basic theoretical tool we have is through Gaussian approximation. Some change point problems are there. I mean, I've worked on some change point problems where we are looking at different series, and then different series have different breakpoints. So for example, you can look at, let's say, the COVID counts in different states or different countries, and they might have different sort of incubation periods. So we want to see if the period lengths are the same for these countries or these states or these regions, or they are differing. Here what we were doing was different cities have different breakpoints, and we were trying to see whether these breakpoints synchronize over this time. And there is an interesting application in gene, like where they look at these breakpoints. Based on these breakpoints, they cluster the genes in different pools, and then they sort of try to see whether these pools do show similarity or not. So this is one question that we are trying to understand, whether the change points are synchronized or not, or if there are not, then how many clusters can we break them into, and what do this sort of different time series are like, how similar they are if the change points are appearing at the same time. If all the change points are appearing at the same point, then they are showing sort of similarity, but if they are not, then in how many ways we can separate this one out. About the forecasting, we
So,
I have
hello, hello.
worked on. Yes.
Yeah, hello. Yeah, so this change point analysis, so what are the tools to do that? Like, how do
So
you
for
understand?
example, you can look at the usual q sum, which is the cumulative sum, and based on the cumulative sum, where the cumulative sum mm, mm, takes a maximum deviation from its expected value, then this is where, like, if there is no change whatsoever, then the q sum test statistic will give you the location for the change point wherever the q sum test statistic is maximized, and based on that you can fit a model for the left, a model for the right, and then you look at these different components. So q sum test statistics is one way of doing that. You can also do it via like a sort of a likelihood based principle. So this sort of change point analysis is very common in time series because there is a natural sequential order, a temporal order, and then you see at which point you can draw a break and then separate out the two parts. uh,
So, yeah, I was just reading yesterday something really interesting about time series that is called the distance time warp function. Okay.
yes.
Uh, yeah. So, is it related to that? Like, we
No,
understand.
distance time warp is like sort of another sort of classifying information about the time series, where you look at two couple of time series and you try to see whether one time series is influenced by the other one or what sort of similarity they have. So DTW usually is used to classify or clustering of time series. Sometimes it is used to do this Granger causality, in the sense if one time series influence the other one. So distance time wrap has probably nothing to do with like change point. Change point is like, you can imagine that you have yi equals rho yi minus 1 plus ei, but the value of rho changes suddenly at one another point. So it's kind of connected to the time varying model, but in the sense that it is more abrupt. It does not change smoothly, it changes
Okay,
like
okay, makes
abruptly.
sense.
So for forecasting, like I was saying, it's probably one of the most important goal of time series. People want to understand what will happen in the future. And so we were like, I have a couple of projects on that, where you look at this black lines. That black lines is the observed data set, and this is in the future. Instead of observing what we will do on exactly yn plus one, my projects were more focused on what happens on yn plus one to yn plus m. So this sort of which is like the next m instances of the time series. So these are important from a strategical point of view, in the sense that you're not interested in knowing exactly what happens tomorrow, but you would like to know what is going to happen in the next 1 month, so that you can plan accordingly. Now these are all predictions, so you cannot say that okay, this is the exact number. So based on this prediction number, you would like to give like a prediction interval around that, so that people have an understanding, okay, with 95% of confidence I know the numbers are going to be vary between these two. So this was one of the electricity pricing data from a country, from a city, I think from Austria, and we were looking at the next few months in understanding, so from January to April, to understand how much electricity consumption will be there in these cities. So I'd like to conclude the talk here by just spatial grid analysis. So this is one of the paper on forest fire. I have not worked on this, but now the dependence, rather than going on xt and xt plus h, now you can imagine you can extend this dependence through a grid, like from a grid point here at the top of this through a grid point here. So it could have like a 2D array of dependence. So based on how far it is in terms of the number of rows and number of columns, the dependence might decay. So there are different interesting spatial models as well. And so there are a few works that I've been doing on spatiotemporal projects, where you have for each data set. So you can imagine in the US map, interestingly, I was just working on this before coming to this talk. In the US map, you can have different counties, you can have different states with different sort of patterns. And then based on that, you'd like to see whether the states show some like sort of a spatial relationship, or they are similar as time series as they progress. So these sort of data sets are called spatial or spatiotemporal data sets, where you have both a space component and a time component inside it. it can go grow more to network where you do not typically have like a time order or like a distance notion. But in a network analysis, that's one other interest of mine in the sense. So these results are all like emanating from some theoretical results based on how you look at this network structures. And so here you can have like a community structure. This is more like a combinatorial model where you have different communities clustered, and then you are trying to see the how these communities sort of communicate with each other, how these communities are different from each other, how the connectivity is varying, and whether it's varying over time. In the sense that initially the community might look like this, they can become more connected, they can become less connected over time. So this is something called like a dynamic stochastic block model. The goal is to identify how these communities are behaving, whether the number of communities changing or not, blah blah blah. And then finally, I would like to conclude the talk by saying something that I've been working on for the past few months. This is very different from what I've been working on previously, but the what I mean, what I really liked about this team of work is no one is actually exploiting the time series analytics on this, the autoregressive analytics on this. So this is called this Adam algorithm. It's an extremely popular algorithm, came out in 2015 or 2016, and in 5 years it got more than 70,000 citations. A sad story is that the proof that they gave in this paper with 70,000 citations, the proof was wrong. I mean, there was another paper that came out back in 2018 or so, which showed a counterexample of their proof, and but the algorithm remained very popular. If you look at the algorithm, you're trying to identify minimum value of some objective function, and the way you do it via this stochastic gradient descent. You look at the gradients of the function, and then you sort of build on recursively on that based on xt plus 1 is xt minus eta times delta fxt. But people have seen like this stochastic gradient descent does not do well in actual neural nets. So people have been like sort of doing modifications, and this Adam and RMS prop, which is a special case of Adam, you can see xt plus 1 is xt minus something here times mt, where mt also have this gt, which is delta fxt. So in a sense, xt plus 1 is an autoregressive process of order 1, where you have an xt and something else. So it's a nonlinear process, but it's not exactly like rho xt minus 1 plus this. But I've been trying some of my sort of an autoregressive analytics on this to identify, can we do something better than this, or try to prove something. Like, you would be surprised to know, even with 70,000 citations in 5 years, which is really huge, like even for the machine learning community, people have not been able to prove this converges in the very vanilla setting. They do assume this model, assume but very strict assumptions. They do assume like tweaks of this model, but they are unable to prove that this will converge to the global minima. So these sort of problems, like in neural net, a lot of mathematics are open, and I believe that there is something that can be done through, like, people have not viewed this through this sort of eyes of like this autoregressive dependence. They have been doing this more traditionally, so there could be something more that are there in knowing about this autoregressive structure. So that's where I'll probably wrap up. Sorry about going over by like 10-15 minutes, but yeah, if you have questions, maybe I can take one or two in the next couple of minutes.
Thank you so much, Vaidya. I really learned a lot from you, Shayada, from this talk.
Thank you,
And
thank you.
yeah, so I also have like believe there's a lot of project ideas over here you have for the students, and they must be thinking about that. So Kapil Gupta has a doubt here that please let us know the title of the other paper. I think that has for 70,000 citations, I guess, Kapil, or maybe the proof, the counter
Yeah,
example.
if you just search for, I think the name is Jingba. I'll just do that. So if you just search that paper should be there, like Adam. Let me give the name, Adam Jing paper. Yeah, so Kingma. I was sorry, I was saying Kingba. Uh, Adam, a method for stochastic optimization. Okay, so
Say
Adam,
these
a method
questions
for
again.
stochastic optimization.
Adam, the method of stochastic
A
optimization.
method for stochastic optimization, that paper. So if you just search Adam paper, you should be able to see the first link that comes, which is an archive link back in 2014, that's cited by 72134. So that Google will definitely show.
Yep. So Obinandan from our batch, like him, stat second year, is also telling it's a very good talk. Diganta sir has told, one of our students, Hemant Bishal, has also told. So yeah, it was a really
Thank you.
nice talk. Yep.
Thank you.
And okay, so any questions, guys, out here? Any questions? So I will wait for another 1 minute for the questions. In the
Okay.
meantime, if you haven't subscribed to this channel, please do subscribe. And any questions? So yes, Uttaran Chattopadhyay is telling that your community detection model seemed very interesting. Would like to
Yeah,
know more.
that's like not exactly time series, but there's a lot of interesting work that's been going on in the last 6 years. Like it's very decent. People have been working on understanding this community, and like there are people from ISI who works on actively on this. So
Yeah, who can you name the people who work actively on
yeah,
this?
so for example, I think Shishendu Chatterjee, then Shormoli Bhattacharya, Shomendu Mukherjee. A lot of you probably know they work on community direction for a long time, and I think Shomendu is like 1 year junior to us. He went to Berkeley, and then
Yeah,
now
yeah,
he's at ISI. So yeah, so there are a lot of people in ISI. Actually, all of them have like some sort of UC Berkeley connection, and they work on this community detection for a long time, and very interesting stream of work, and it has a communal flavor, so you might like that. Yeah.
yep. So Uttaran is asking a question. In the meantime, Hemant is asking how many variations. How do we account for the variations? Wait,
Yeah,
how
there
many
is.
variations can we through economic new? How news? How do we account for such variations? Yep.
Yeah, it's difficult to take care of all the exogenous variables. Like you can never do that. Like you sometimes look at how the econometric, like the how the econometricians or like the how the economics people are saying, and then you can do a statistical test. Like it's difficult to understand exactly which variables to take care of. Like you can think about like jointly modeling some of these variables sometimes, in the sense you can model the same variable for the US data sets and the Europe data sets, and then see how they affect each other. Like I was saying, this multiple series can sort of co-move, and you need to take care of how they co-move together, and to understand how they influence each other. But it is difficult to just, I mean, I cannot give a very short answer to that, like how to know exactly which variable to take care of. The way I analyze this sort of model is that you look at this sort of functions, then you see interesting changes, and then you try to go back and retrospect. Okay, why is there a change? Is there something that happened in the backwards, or some sort of political movement that sort of influenced that? Or like let's say due to the pandemic, a lot changed. Due to the financial crisis back in 2008, a lot changed. So then can that explain this sort of phenomena? So these are the questions that you can understand, like you can do in retrospect, and then you can fit separate models for that.
Okay, perfect. So yeah, Shohom is asking. He's off from also IMSAT second year our batch. A very insightful talk,
I
Sharda.
know Shubham, yes, yes, I know Uttaran
Yeah,
as well, yeah. But,
yep.
will that sort of situation that can be tackled by a spatio-temporal model? That's like, so the question Uttaran has is that it is changing its position over time. So if you look at this sort of spatio-temporal type of like the one that I talked today is not like that. You have fixed grids, and in each grid you observe a time series, and then you are looking at similarity of these time series in how they're, like if they're on neighboring grids, then they are probably closer. If they're very far apart, then they're probably not that close. But the way Uttaran is saying is like also called spatiotemporal analysis, where you look at like sort of a path-based analysis based on exactly where it is at which time point of time. So there, in that case, you note x, y, and the time, at each time instances wherever they're observed, and then based on that you can do that. So you can actually do this sort of analysis. People do that in geography or like in criminology type of analysis, where they try to understand this sort of cluster hotspots where these crimes are happening. So yes, there are quite a few analyses. So maybe you can look at like spatiotemporal clustering. That will give you some insights about how to analyze that.
Thank you so much, guys. And also, our students Spondon and Rodnodeep from ISI, our junior, has also told very insightful and beautiful
Right.
talk.
Thank you so much.
Right.
Thank you. It was nice talking to you. I know the
Yeah.
situation back in Kolkata is not really great. So I hope you all are safe. Take care. Like sort of, yeah, it's been troubling. Like I was also supposed to visit Kolkata this summer, but probably I won't be able to. But yeah, hopefully you are all safe and you can take care of your near and dear people. Yeah.
Yeah. Thank you so much, Vaidya Sharda, for being for waking up at 3:30 a.m.
No,
there.
that's all right. That's
And
not a problem.
I don't know whether it's a habit from ISI or not,
It is
but yeah.
indeed a habit from ISA, but if it were in ISA, I would probably stayed up. But now I cannot. So that has changed. Yes.
Okay, lovely. Okay, so thank you guys, and yep, I hope many of the people will collaborate with in the future, and
Hopefully,
I
I
think
hope
this
so. Yes,
discussion
I'm
will
looking
be
forward.
leading some great projects and research out there. Thank
Sure.
you guys for your time,
Yes.
and yeah, thank you so much, guys. So yep, I'll see you soon in the next webinar.
Thank
Thank you.